Merhabalar. Burada olmak çok güzel. Kaytas'a bu hoş daveti için çok teşekkür ediyorum. Konuşmamı İngilizce yapacağım. Welcome everyone. Today I'm going to talk about how we can enable 5G networks and the importance of edge cloud in the concept of 5G. And I will also talk about, as Guru mentioned, our next project within ONF, which is the creation of a multi-access edge cloud. Okay, so the outline of the talk is as follows. I'm going to first make the case for an edge cloud, why telcos really need one. And then I'll introduce ONF's Chord as the 5G enabling open source edge cloud platform. I will talk about Chord, I'll introduce it, and I will also give you a status of where we are today. I will also briefly talk about where we're going with Chord, where things are, where we're going to be focusing on. And then I'll introduce ONF's Open Edge Cloud platform. And I will try to introduce it using two perspectives. I'll first start with a bottom-up perspective. So with the understanding of what Chord is through Guru's presentation and how I'll explain Chord, I will stress exactly what additional features need to be included into what we have today to make our vision of Edge Cloud possible. But then I'll also talk about a perspective from top down. So once that Edge Cloud is there, how can actually telcos use to monetize it? And more importantly, how can developers actually use that platform to develop new services that they can then present to their subscribers all around? And I'll end my talk with a few takeaways from what I'm trying to really convey. So let's start with why we need the edge as telcos. So for that, let's first talk about the cellular evolution. So since 1980s, cellular networks has been part of our lives. And we've seen over the last 40 years that the cellular network evolution was that every 10 years, just about every 10 years, we had a new G. The 3GPP standards evolved, and we started with 1G and it evolved, and right now we are at the cusp of 5G. So over the last 40 years, the evolution of standardization focused on two distinct services, voice and data, broadband data. And over the last 40 years, the focus was first enablement and then scaling. But as a consequence, as end users, we started using and demanding more higher bandwidths and more of that. And it became really an integral part of our lives. So that actually introduced a huge burden on telcos. They have to increase their investment continuously to provide the service that we want. But when you think about it, the real services value chain is sitting on top of the telcos, and telcos are not part of it. When we actually use our phones more and more, we're using it to connect to Netflix. We're using it to look at Facebook or Twitter, or to listen to music on Spotify. And that's where the services value chain is. So as a result, what we're seeing is the annual revenue per user globally for the telcos has been on the decline for a number of years. So that brings us to 5G. 5G really needs to be different than the prior generations, if for nothing else, for economic reasons. So it needs to be a business enabler. It needs to be sort of a disruptor for the services value chain. So for that reason, for the first time, 3GPP has decided to extend the services reach for the cellular system when building a new standard. So for 5G, the optimization of the cellular network is no longer just for voice and data. There are additional services that the network, the cellular network, needs to be optimized for. And these services, in addition to the traditional ones, are low latency services that also include ultra reliability, but at the same time, massive machine type communications or massive IoT. So we need to start thinking about these services as well. So what does that really mean? That really means that we need a new architecture in deploying 5G. And at the core of that architecture is really the edge cloud. So let me try to make a case of why exactly we need 5G, within 5G, the edge cloud for these new types of services. And it is best explained using actually what the Amazon CTO describes the edge as. So Werner Vogels, the Amazon CTO, calls the need for the edge cloud using laws. And he calls them laws because regardless of the advancement in technology, these requirements are here to stay. And the first law is the law of physics. And that actually means that we are burdened by the speed of light. So if we want a low latency communication, and if actually data is generated at the edge as end users, then we need to be able to process that data at a place that is as close as possible to that end user. So that necessitates, the speed of light necessitates that we need an edge cloud. The second is the law of economics. So more and more, we're seeing that data is being generated at the edge. So traditionally, when you think about Netflix, Facebook, it is the other way around, right? We have a centralized location, and as end users, we've been the consumers of that content. But more and more, especially with IoT, you are going to see more and more data generated at the edge. And more, the locally generated data is going to be consumed locally as well. And the increase in this usage at the edge is growing today at a rate that is higher than the bandwidth increase at the core of the internet. And this is because of IoT. As of today, we have more IoT devices than mobile phones in the network. So that actually tells us that economically, if we know that data is generated at the edge and it's consumed at the edge, it is better to actually localize the traffic there so that we don't necessarily have to overburden the core network. So that requires a compute at the edge. And the last but not least is the law of the land. So there are some use cases where you want actually, for legal reasons or for security reasons, you want to isolate where you want to process that data. And that also means you need an edge. Think of an enterprise solution. So the company wants to actually keep their data local in their campus, and that also requires an edge. So with that in mind, now that we've established that we need an edge in 5G, let's talk about ONF's Chord, but with the mobile flavor as an open source platform for the edge cloud. So as Guru mentioned, Chord is really built on the pillars of utilizing commodity hardware. So we're using white box switches and off-the-shelf servers to realize an edge cloud. And in addition, unique to M-Chord, we have mobile-specific services as open source as part of this platform. So today we have actually the core network, EPC, as open source. And in the near future, hopefully, we will extend to that the virtualized component of the RAN as well. So this is a platform where effectively both the core network and the virtualized component of the radio access network would reside. But in addition, it would also be a place where these latency sensitive services would reside as well. And it would be basically all these services and virtualized network functions would be virtualized, and they would be running on servers, and these servers would be interconnected by a leaf-spine fabric, which is SDN enabled. And the SDN enablement gives the telcos power to control, to have more control over the fate of their own network. But at the same time, and equally, if not more importantly, especially in the context of cellular networks, some of the virtualized network functions, especially in the user plane, we realize are very I/O heavy. So when you virtualize these functions, then a CPU, an x86, is not the best processor to run this on. You are better off actually utilizing a processor that is optimized for an input-output heavy operation, and that would be a switch processor. So with P4, now you can do that. So this would be a place where some of our user plane functionalities are realized right on switches. And another pillar for mChord is that it, like Guru mentioned, the access, the RAN part is also SDNized. So that allows you to turn this into a policy-driven programmable entity, and at the same time, we can have dynamic, automated services. And Kite has mentioned that at Argela, during my actually post in Argela, we have developed PROGRAN, and PROGRAN would be an example of the capabilities that a programmable RAN would introduce. And last but not least, this would sit on an open source platform that allows for a dynamic instantiation and control of subscriber-based services and service chains in a cloud fashion. And I mentioned that the platform also brings in open source core, and in the future also RAN components. All right, so I talked about disaggregation. So this is actually from an end-to-end point. It's a busy slide, but from an end-to-end point, this is how a 5G network would really look like. In this case, the user equipment is going to be a lot more diverse than it is today. So it is not just going to be handsets, but lots of IoT devices, autonomous vehicles, etc. And the RAN itself is going to actually be disaggregated into three components. We're going to have a radio unit, we're going to have a distributed unit, and we're going to have a centralized unit. And also we're going to have the core network, disaggregated into components. We're going to have a bunch of network functions for the core control plane and a bunch of functions for the core user plane. So in that sense, when you look at this, we have a disaggregation of RAN. But that also brings in a distributed RAN solution. So while some of the components are going to be geographically distributed, some of the components, specifically in this case the centralized unit, will sit at the edge, and the distributed units would pool these components. And likewise, the core itself is disaggregated, but it needs to also be distributed. And this time around, the distribution is between the edge and a centralized cloud, so that the user plane functions that that really need, that are needed for latency sensitive applications would be pushed to the edge, whereas the control functions could actually pool a number of these user plane functions together, so that that means they would be residing at the centralized cloud. So effectively, we're talking in terms of 5G architecture, a disaggregated but also distributed architecture. So what are the consequences of this for the edge cloud? That means the edge cloud should not only provide an environment for the virtualized components to run, but at the same time, I need to be able to very quickly and easily connect to the centralized cloud and other edge clouds. So the inter-cloud connectivity is a very important aspect here. All right, so with that, let's talk about where we are in terms of mChord. And a good example of where we are is the last demo that we had in Los Angeles at Mobile World Congress Americas just a month ago. So for that, we have the leaf spine fabric. On it, we have a number of servers, and connected to this, we have the access unit, which is the base station, and it is a programmable one. So we actually, for the first time ever, we created a cloud native edge. So that means all of the virtualized components that I mentioned are containerized. So these are all Docker containers, and locally, the edge uses Kubernetes to manage these containers. This management includes the instantiation of all of these containers, but also scaling up and down. And on it, we have a number of containers, and these containers are basically the operating system for the edge. As Guru mentioned, it would be XOS as the services controller and ONOS as the SDN controller. But in addition, we would have the core network user plane and control plane functions, as well as the applications that telcos create, but this is also an environment where OTT applications could reside as well, as for latency sensitive applications. So an environment that uses service mesh to sandbox these applications within the edge cloud is also there. And we also have analytics solution. So in a cloud native sense, we use, for example, Prometheus to collect the status of the CPU usage and the memory usage. And we also use another analytics engine to look at the network state. So the base station, all the base station, controllable base station, provide us the network state for on a per subscriber basis for the wireless link. And then ONOS provides us the fabric state. So all of that is used in a closed loop fashion to automate the network. And so XOS then oversees the overall services across all, and ONOS actually is used for controlling the fabric. It is used to control the RAN as well as the core. And then in a hierarchical scenario, you would have, within Turkey, for example, Türk Telekom might have thousands of these edges. There would be a global orchestrator. As an example, in the demo, we used ONAP, and that each edge would adhere to a global orchestrator. So this demo actually used the latest version of Chord. It was using the next generation SDN for the fabric, which was P4. And like I said, it was a truly cloud native solution. And it used service mesh for OTT service isolation. We had our own open source EPC that we leveraged, and we had closed loop analytics as part of the solution, so that changes in a per subscriber quality of service or the utilization, CPU utilization of any one container could actually trigger a change in the network management. We connected all of this to ONAP, and we did network slicing. So the network slicing was end-to-end, so we included PROGRAN as well as its capability for core network slicing. The ONAP and the network slicing aspect of this demo was accomplished by Netsia in this example. All right, so what are the next steps for Chord? The first one, as Guru mentioned, is ORAN. So those of you who may not know what ORAN is, ORAN stands for OpenRAN, and it is a new, just like ONF, it is a new operator-driven, operator-led consortium. So there are about 12 operators already part of ORAN, and their mission is to develop a disaggregated but also controllable RAN solution. Once the operators decide on how they want to go about it, they will push for these changes in standardization. Very, very briefly, the disaggregation of the RAN, like I mentioned, is the radio unit, distributed unit, and the centralized unit. And the programmability comes with a controller. And that controller then also on the northbound speaks with a global orchestrator like ONAP, so that an operator can actually push these policy-driven programmability across a given geographical region. So within this, what we plan to do as ONF is to develop an open source controller for ORAN. Next, we also plan on utilizing our ecosystem, just like we have done with EPC, and develop the software stack for the centralized unit. And for the distributed unit, we plan on doing exactly what Guru has mentioned, create a white box solution for the DU, and also develop the software stack as open source. And ONF is a great place for this because actually, as far as the controller is concerned, the starting point for the ORAN specifications is called XRAN. And we already have an ONOS-based XRAN controller, actually the only controller in the that has been advertised so far for XRAN has been ours. Then it would be an easy progress for us to move this to ORAN. The software stack, like I said, we have experience through EPC on how to leverage our ecosystem, so we could do the same for that as well. And for the distributed unit, we have actually a number of our vendors showing initial interest in open sourcing their initial solutions, giving us a really solid starting point. The second advancement for Chord is going to be at the core side. As I mentioned, the core network itself is disaggregated, even in LTE. So we have, starting from release 13, we have a user plane, control plane separation, within the ONF realization, we can have some of these user plane functions be running right on the switches. Those of you who are in wireless know how the LTE EPC is really connected and how it works. So within this, we have implemented this EPC, but with some additional features. The additional features are actually turning the core itself into a programmable entity. And we do this in two different ways. One, we create a controller for the core that enables policy-driven billing and charging operations for the telco. And then the second controllable entity is a slicing controller, which effectively is PROGRAN. So we have the disaggregated containerized EPC components available today, and it ships actually with the latest Chord release. All right, and as you know, with 5G, the core network itself is evolving. So within the evolution, some of the VNFs are being further disaggregated towards more and more like a microservices architecture, and some of them are changing names and adding some new functionalities. So what we're planning on doing within Chord is to evolve our open source EPC to NG core, the 5G core. And while doing that, maintaining our programmable enhancements to the overall solution. All right, so what I want to now focus on is the Open Edge Cloud. When you think about the Edge Cloud, really, as far as ONF is concerned, the vision is that there are really three really important components that we have to pay attention to. First, most of the telco operators would have multiple access technologies for which they have subscribers. Think of Turkcell or Türk Telekom. They both have both wireless and wireline services. So we need an edge cloud that actually starts treating access as a service. And as such, you can host these different access technologies in one cloud environment. But additionally, I mentioned that one of the key features for 5G is to distribute the disaggregated core and RAN across multiple clouds. So that means the inter-cloud connectivity should be an integral part of an edge cloud offering. And third, this is a cloud. And when you think about a cloud subscriber is one that utilizes the cloud resources. So in that sense, the multi-tenancy for the edge cloud needs to be two-dimensional. This is a telco-owned cloud, which means the traditional subscribers, which are the end users, like all of us, will still be around. So that is one dimension of multi-tenancy. But the second dimension is this is a cloud. So as such, telcos should be able to monetize it just like today's cloud providers can. So that requires a platform which they can actually start sort of selling in a way as platform as a service to cloud subscribers. So as far as inter-cloud connectivity is concerned, at ONF, this is the first attack for the Open Edge Cloud architectural solution that we've started to sort of laser focus on. And for that, we are leveraging service mesh. Those of you who may not know what service mesh is, you can effectively see this as a layer 7 SDN. So what it does is through it, it isolates a developer from really knowing the innards of the plumbing between multiple cloud connections. So a developer can actually just focus on a distributed solution, and then the service mesh would handle everything that sits underneath. For that, our first POC, our first planned POC is focusing on EPC along with a streaming multimedia service. So the EPC, consider an EPC where the VNFs are distributed across edge and central cloud, and a multimedia solution where we have a CDN and an archive, again, separated between edge and central cloud. So the service mesh would actually create the connectivity and in a way that is agnostic to the developers. The top-down perspective is really focusing on how telcos could monetize the edge. So telcos current monetization environment is based on subscribers like you and I, or maybe enterprises, but it's the end users. But effectively, if you have really truly an edge cloud, this should be a cloud, right? So effectively, you are providing an environment that is uniquely a place where access and cloud meet. So that means effectively telcos can start thinking of this as platform as a service. And this platform as a service would be an environment where connectivity-based services could be developed by telco's own developers, or by MVNOs, or by third-party services. And the APIs for the platform as a service could be utilized to take advantage of the cloud environment. So let me give you a couple of examples to make this point more clear. Let's think of, for example, the first possibility, which is connectivity as a service. Think of an end user service, and it could be an IoT service, for example. And that IoT service needs connectivity between the IoT users and its service, virtualized service, wherever that may be. So for that, it needs to effectively use these APIs to ask from the telco, and this is something very akin to what just Paul Doney has mentioned, to tell the telco, oh, I need assurances of this much latency. I need guarantees of this much throughput in the connection. And by the way, I also want just wireless, and wired is not an option. So you have these different options that you can pick and choose, and that gives you a unique flavor of connectivity for your own use case. The second one is telemetry as a service. So as a cloud environment, now telcos have full control over the network state and the infrastructure state. By that, I mean, for example, in a wireless scenario, they know, and they can actually keep the state. They know exactly which users are connected to which base station. They know exactly what their average bit rates are. They also know the mobility patterns. They also know for each service how much the CPU is being utilized, how much memory is being utilized. So in an abstracted way, they can actually let third-party applications subscribe to this data. So based on that, the services can actually further optimize themselves. The next one is service mesh as a service. So if I'm a third-party software developer, for example, if I'm someone similar to Netflix, then I will need a local content location as well as a store which would sit in a public cloud. So rather than really figuring out how I actually do the interconnects, I let the telco deal with that. And using a platform API, I can just ask telco to provide me with that connection, and I don't have to worry about it. And last but not least, another example is machine learning as a service. So this would be very, very similar, those of you who know, to Amazon's offering of Greengrass. So they have a rich library of machine learning functions, engines, and inference engines that are available, and these would be basically leased out to customers who want to utilize it. And this would be an opportunity for telcos to repeat that in this environment. So let me end the talk by giving two example use cases. Think of autonomous driving. So effectively, in an autonomous driving, you would have a bunch of autonomous vehicles, and these vehicles would need to connect to an inference engine via an IoT hub. But the interconnect in a wireless environment has to go through a cellular user plane. So here, the service graph that we're talking about is a cellular user plane connected to a hub, which is connected to an inference engine. This, for latency purposes, need to reside at the edge. But at the same time, the core user plane needs to connect to the core control plane. And that actually could be residing at the telco central cloud. And if the autonomous driving example is owned by a third party, their machine learning engine could be actually residing at a public cloud, let's say Google Cloud. So in that sense, as third-party application, what I need from a telco is, one, connectivity as a service, so that IoT or vehicles are connected to my IoT hub in the way I want them to. I would need service mesh as a service so that I can interconnect my inference engine to my machine learning engine, which resides in Google Cloud. And I potentially would need also telemetry as a service so that I can fine-tune my inference engine as time goes by. And another example is public safety. So in this case, the third party would be maybe the city municipality, and they would want to connect motion detecting cameras to the edge. And they would want to automate this operation so that whenever there is a suspicious activity that is automatically detected, the nearest police car is alerted. And again, that requires from the telco all of these as a service applications for enablement. So what are the key takeaways then? So an edge cloud is absolutely necessary to start offering delay-sensitive services to end users and enterprises. And this edge cloud is inherently different than today's cloud. So you can't just pick today's cloud architecture, move it to the edge, and hope that it'll solve our problem. Because this is where really connectivity meets the cloud. And it's a distributed compute paradigm, so inherently it is very, very different than today's centralized cloud solutions. ONF's Chord leverages commodity hardware, disaggregation, virtualization, and programmability to provide telcos with a compelling solution for the edge. And this edge is also introducing a platform that enables new monetization techniques for the telcos in terms of more cloud-like solutions. This is an environment where you have, as I mentioned, a two-dimensional multi-tenancy paradigm. So you have tenancy in terms of subscribers and tenancy in terms of cloud subscribers. Telcos can now offer lots of as-a-service solutions to third parties with this cloud environment. And as Guru mentioned, Turk Telecom and Argela have been very prominent members at ONF, and I look forward to continuing to work with them towards field trialing both Chord and Edge Cloud. Thank you.
Teşekkür ederiz Doktor Sunay'a. Sağ olunuz efendim değerli katkılarınız için.